So we get into another section of trigonometric substitution. So now we shall look at numbers that actually require the Weierstrass substitution. So for this first set, we're going to look at those numbers that require the substitution t is equal to tan x. So it can also be called tangent substitution, but it's not to be confused with the other form of the one that we've actually shown before, because the other one is a restricted tangent substitution that we've looked at before, probably in video number 6. So this is different, and we actually have to understand when this is useful. So the tangent substitution is also called Weierstrass substitution. So this substitution is a trigonometric substitution. T is equal to tan x. So this is actually what we're going to be basing on. So we're going to be letting t to be equal to tan x in these numbers. So this is very useful for integrals involving a simple rational expression in even powers of sine x or cos x in the denominator. So there are those that where we have a sine squared x and a cos squared x, probably adding or subtracting or probably something like that in the denominator, and you realize that probably no other method from before could work. We couldn't use substitution, we couldn't use any other. So basically when you get stuck on a number, like as I'll show you in this section, you'll actually apply Weierstrass substitution. For now, we'll have numbers where there is a power of sine and a power of cos, and then also in cases where we actually have some double angles like sine 2x and cos 2x. But basically this will make sense as we look at different examples. So basically the numbers may look like this. So probably you actually have some variables at the bottom. So you have functions where we have sine squared x, we have even powers of cos x and sine x in the denominator. So basically here there is no other method that will work except Weierstrass substitution. So we can integrate it in 3 steps. So first step, write the integrand in terms of the new variable t. So to do this, use the special right-angled triangle. So I'll illustrate that in this section. So step 2, integrate with respect to the new variable t. Then step 3, write the final answer in terms of x using the fact that t is equal to tan x. So this will make perfect sense when we look at an example. So look at this question right here. So being told to evaluate the integral of 1 over 1 plus sine squared x. So someone may have thought of maybe use substitution or probably changing this sine squared x into something, but you actually realize that all that will be in vain because you'll not be able to still do the number. So this can only be solved using the substitution t is equal to tan x. So how do we do this? We're going to let t to be equal to tan x, and then we're going to differentiate this. So you can actually say that dt dx should actually be equal to sec squared x, and then if we can also see that we can actually put this sec squared x in terms of t. So it's sec squared x we know is 1 plus tan squared x. So this is what we converted to, and then next we can actually see that because we had said that t is equal to tan x, we can replace the tan x here with the t, so we have 1 plus t squared. So if we make dx subject, dx should actually be equal to dt over 1 plus t squared. So now that we have that, now the next thing is we need to find out what sine x is actually equal to. So if t is equal to tan x, we can actually find what sine x is in terms of t. But let's find out what that is. Now this is going to be equation 1, so let's make use of this. So we can already see that t is equal to tan x. So what this also means is that tan x is equal to t over 1. So you can represent this on a right-angled triangle. So that means we're going to represent it where t is going to be opposite and 1 is going to be the adjacent. So if we have the angle x, as we've said here, we shall see that the opposite is t and then the adjacent is 1. So what's left is to find that hypotenuse. So from Pythagoras theorem, a squared plus b squared is equal to c squared. We'll have 1 squared plus t squared being equal to c squared. And then if we make t squared if we make c squared the subject, it should actually be equal to root of 1 plus t squared. So that means our hypotenuse is root of 1 plus t squared. So therefore, sine x, which is what we're looking for here, sine x, which is actually equal to opposite over adjacent, that is t over root of 1 plus t squared, as you can see, is going to be equal to that. Now, we need actually what sine squared. How about what sine squared x is equal to? So sine squared x should actually be equal to the square of this, which should actually be equal to t squared over 1 plus t squared. So now that we have that out of the way, we can actually see that this is going to be our equation 2. So we now know that, and therefore we can now go back to the main integral. So the integral becomes integral of 1 over 1 plus, so where there is sine squared x, we actually put t squared over 1 plus t squared. Then times, so where there is dx, we actually replace that with dt over 1 plus t squared. As you can already see, this shall actually go to the numerator. So basically we're going to leave the dt here, but remember this is basically 1 over 1 plus t squared. So we have 1 plus 1 over t squared at the numerator, and then this is at the denominator. So we're going to find the LCM at the denominator. So the LCM is 1 plus t squared, and then 1 plus t squared divided by 1 is going to be equal to 1 plus t squared. Then multiply that up, and multiply it up, and we'll have 1 plus t squared plus this t squared, and then we'll have something like that. So basically when I add this, I'll have 1 plus 2t squared. Now the next thing I can see is this and this cancel, so I'll be left with 1 over 1 plus t 2t squared. So now that we have it in this step, we can actually see that now this can actually be used using the tan trigonometric substitution. So now we can actually see that now this has to be expressed in terms of a square. Now we know that the square, when we square root of 2, we get this 2. So basically we will have something like this. So root of 2t squared, because when we put that squared back in, it will give us back our 2t squared. So now that we have it in this format, we can now apply the tan trigonometric substitution. So by tan trigonometric substitution, we can see that root of 2t shall actually be equal to tan theta. So if you've not understood what this tan trigonometric substitution means, you can actually go back to my video. I believe it's video number 6 on integration of that shows you about tan trigonometric substitution. So this is what we have. So we make t the subject, and t shall actually be equal to 1 over root of 2 tan theta. Then if we differentiate that, dt the theta shall actually be equal to 1 over root of 2 sec squared theta. So make dt the subject, and dt shall actually be equal to 1 over root of 2 sec squared theta d theta. So let's solve for theta. As you can see from right here, you can actually say that theta shall actually be equal to tan inverse of root of 2t, root of 2 times t. So therefore our integral becomes this. So I have 1 over 1 plus tan squared theta times 1 over root of 2 sec squared theta d theta. So therefore we can actually also see that this is actually going to be equal to sec squared theta, of which this and this shall cancel, and then we can actually pull out 1 over root of 2 out of the integral. So we'll have 1 over root of 2 into the integral of 1, because what's left in the inside is 1. So the integral of 1 is theta, and then therefore we remember that theta is tan inverse of root of 2t, so we put that back in, and we'll have 1 over root of 2 times tan inverse of root of 2t. So open those brackets. But before we do that, let's see, remember t is actually tan x, so place that in, and then we'll have 1 over root of 2 tan inverse of bracket root of 2 times tan x plus c, and that is the answer. Let's look at another question. So in this question, we'll be told that using the substitution t is equal to tan x, evaluate the integral of 1 over 4 cos squared x plus 9 squared x dx. So what do we do here? So this is also going to require Weierstrass substitution, where we let t be equal to tan x. So we've already been told to let t is equal to tan x, so dt dx from here, you can see that it is sec squared x. Then we know that sec squared x is the same as 1 plus tan squared x, so that's what we'll have. And then we can remember that t represents tan x, so therefore we can have this as 1 plus t squared. And then if we make dx subject, dx shall actually be equal to dt over 1 plus t squared. So now next we shall remember it again, that this can actually be expressed as tan x being equal to t over 1, and then you can place that in a right angle triangle. So the angle is x, and then the opposite is t, and the adjacent is 1. So from Pythagoras theorem, we can actually find the hypotenuse. So if we make c the subject, she shall actually be equal to root of 1 plus t squared. So we can place that right there. So now in this case, we need to know what cos squared x and what sin squared x will represent. So therefore sin x, we can see sin x is opposite over hypotenuse, so we'll have sin x being equal to t over root of 1 plus t squared, and then cos of x is actually adjacent over the hypotenuse, so we'll have it as 1 over root of 1 plus t squared. So you can say that sin squared x should actually be equal to the square of this, which is actually going to be equal to t squared over 1 plus t squared. So that's going to be our equation 2. And then now let's also find the squared, of course. So when we square that, we'll have 1 over 1 plus t squared, and then therefore this shall actually be our equation 3. So now to know what sine squared x and cos squared x are in terms of t, we can now replace that and put them back in the integral. So when you put them back in the integral, this is what we'll have. So next we can actually start solving. So you can actually say that this value here, 1 over 1 plus t squared, shall actually go to the numerator, and then we shall leave the dt right there. So this is what we have basically. So multiply the 4 in and we'll have 4 over 1 plus t squared. Multiply the 9 in and we'll have 9t squared over 1 plus t squared. So you can actually see here that the denominators are the same, so that means you can actually combine those. So we'll have them as 4 plus 9t squared over 1 plus t squared. And then you can actually see that the denominators of the numerator and the denominator will cancel, and then we'll be left with integral of 1 over 4 plus 9t squared. So now this can actually be solved using trigonometric substitution, but for now let's first factorize out the 4. So when you factorize out the 4, we'll have it being into 1 plus 9t squared over 4. But you can see that 9 is the same as 3 squared, and then 4 is the same as 2 squared. So we can combine those and we'll have them as integral of 1 over 4 into 1 plus 3 into bracket 3t over 2, then square that bracket. So now by tan trigonometric substitution, we can say that 3t shall be equal to tan theta. Then let's make t the subject. T shall actually be equal to 2 over 3 tan theta. So if we differentiate that, dt theta shall actually be equal to 2 over 3 sec squared theta. So make dt the subject and dt shall actually be equal to 2 over 3 sec squared theta d theta. Then if we solve for theta from right here, we can actually see that theta shall actually be equal to tan inverse of 3t over 2. So now put all those things back into the integral and we'll have them as 1 over 4 into 1 plus tan squared theta times 2 over 3 sec squared theta d theta. And then what we can already see is that some values cancel. But before we do that, let's just multiply all these values. So we shall have 2 over 12 being pulled out of the integral. And then sec squared and this sec squared shall cancel and we'll be left with 1. Then 2 over 12 is the same as 1 over 6. So we have 1 over 6 into the integral of 1 d theta. And now if we integrate 1, we get 1 over 6 into theta times theta plus c. But remember, theta is tan inverse of 3t over 2. So we put that back in and we have 1 over 6 tan inverse of 3t over 2 plus c. But also remember, t is representing tan x. So therefore we have 1 over 6 tan inverse of 3 over 2 tan x plus c. And that is the answer. So question number 3, we're being told to evaluate the integral of 1 over 5 plus 4 cos 2x. Now in this case, we've actually been given this in terms of a double angle format. So what do we do? So here, we'll actually have to integrate it this way. So we have 1 over 5 plus 4 cos 2x dx. So now we're going to let t be equal to tan x. And now we're going to remember something very important. Before we do that, let's first solve this. dt dx should actually be equal to sec squared x, of which sec squared x is the same as 1 plus tan squared x. And then that can be 1 plus t squared, of which dx should actually be equal to dt over 1 plus t squared. So this shall be equation 1. And then now we're going to remember from trigonometry t formula to actually simplify this. So for double angles, remember double angles cos 2x should actually be represented as 1 minus tan squared x over 1 plus tan squared x, which is actually 1 minus t squared over 1 plus t squared. So remember this from t formula in trigonometry should actually simplify this process. So now we're just going to substitute in directly. So we have the integral of 1 over 5 plus 4 into 1 minus t squared over 1 plus t squared times dt over 1 plus t squared. So this is how we can represent it right now. So now this can actually be taken to the top. 1 over 1 plus t squared shall actually go to the top and we shall leave dt right there. And then right here we shall actually find the LCM. So when you find the LCM shall actually be equal to 1 plus t squared. Then when you do that, we shall have 1 plus t squared dividing by 1 is 1 plus t squared. So we're going to multiply it to this 5. And then the 4 shall be multiplying the 1 minus t squared at the numerator. So next thing we can see is that this and this cancel. So 1 plus t squared and that cancel. And then this is what we're left with. So the next step is to open brackets and we'll have 5 plus 5t squared plus 4 minus 4t squared, of which that is the same as the integral of 1 over 9 plus t squared. So I can already say this number will also require tan trigonometric substitution, but before we do that, let's first factorize out the 9. So we'll have 9 into 1 plus t squared over 9. But remember, 9 represents 3 squared, so we'll have that. So when you combine the square of the t and the square of the 3, we can actually see that we have t over 3 bracket squared like that. And then by tan trigonometric substitution, we can let t over 3, this value in the bracket, be equal to tan theta. And therefore, if we make t the subject, t shall actually be equal to 3 tan theta. So dt the theta, which is the derivative of that, shall actually be equal to 3 sec squared theta. Dt shall actually be equal to 3 sec squared theta d theta. Now let's solve for theta from right here, and you can see that theta is actually basically tan inverse of t over 3. So when you put all those back in, we have the integral of 1 over 9 into 1 plus tan squared theta times 3 sec squared theta. But remember that 1 plus tan squared theta is the same as sec squared theta, so this is what we'll have. So you can say that this and this will cancel, and we'll pull a third out, and we'll have a third into the integral of 1d theta. So now we'll have a third times theta plus c as the integral. And then remember that theta is actually tan inverse of t over 3, so we put that back in and we'll have this. Then we also remember that t is representing tan x, so when you put that back in, we have a third tan inverse of bracket tan x over 3 plus c, and that is the answer. Alright, so next I have an exercise for you. It's an exercise of basically 4 numbers that I encourage you to try out. So the answers are basically on the right hand side of each question. And I believe that after you've tried this out, you'll actually have a better understanding of this form of integration where we let t be equal to tan x. Thank you for watching. Thank you so much for watching this video. I hope the video really helped you. If you did, feel free to tell me below in the comments. I'll make sure to get time to read through your comments and to reply to you. And also, if you're new to this channel, I encourage you to join the community by subscribing. And then make sure to hit the notification bell so that you get updated every single time I upload a new video. Again, my name is Emmanuel Olega. Thank you so much for watching. See you in my next video.